And we've talked a little bit about this. Most of the time, things can't grow exponentially forever. They level off. And there's different reasons why they level off. So here we go. A logistics equation is going to model that type of growth. It says here some populations initially have a rapid growth, followed by a declining rate of growth due to conditions that inhibit growth. We can model this type of growth pattern using logistic curve function, such as, and we have two examples here. So this one has our new favorite number e in it. And this one, these two parts should look really familiar. Yeah. We've been doing those with exponential functions. So, these formulas, what do all those letters mean? So M is going to represent the maximum growth. So if we have a population of 10,000 deer, and they're dying off, how many deer can die?
10,000.
Yeah. Okay? So, that actually, yeah.
Well, they could reproduce.
That would be maximum decay.
Oh, that's true. That may have been a bad example. We'll do a good example in just a second. Okay. A in both of these equations is just a constant, and K is a constant in this one. Now, B in this one is also a constant, and X represents our time. So here we have T for time, here we have X for time. Okay, so these are the two models that we're going to be using for today's lesson. Let's look at problem number 1. It says, on a college campus, 5,000 students, one student returns from vacation with the contagious flu virus. The spread of the virus is modeled by this function. Okay, now, the limit to growth, or the maximum growth, would be 5,000 students, right? That's the greatest number of students that could actually catch the flu, because that's all the students we have. Does that make sense? Okay, so even if we're growing exponentially right here at 5,000, we're going to level off, aren't we? So it's kind of like an asymptote up here, isn't it?
Wait, so it's not an asymptote, but it's almost like an asymptote.
Yeah, because we could actually get to the 5,000. I mean, in reality, it's possible. Mathematically modeled, it's an asymptote.
Okay.
All right, where Y is the number that are infected after T days. So college classes will cancel when 40% of the student population becomes ill. So part A, how many students are infected after 5 days? What do you guys think we do with this?
Plug in 5 for T.
Plug in 5 for T. Please do that. Show your skills. Yeah, it's negative 0.8.
Oh, 3.
Yeah, it's tiny on your paper. Okay, so we've got 54 students that are currently full-fledged flu. That's easy to say. All right, and we've got one that's catching it, but they're not there yet. So we have 54 infected students. If it's exponential growth, we would round down, right? Okay, now part B. After how many days will the college classes be canceled? So this is going to take some thinking. Let's give us a little more space on my paper.
Wouldn't as more students get infected, others would just get immune from having it, then it would go away?
Okay, that's not, it's not the same.
Is it possible? Yeah, but the flu lasts a long time.
Like a
This is not-
week, 2 weeks.
Okay,
This is a
so
hypothetical situation.
it is hypothetical. It certainly is. All right. So if we'll cancel classes at 40%, what is 40%?
Of 5,000.
5,000. 2,000. So when this equals 2,000, classes will be canceled. Okay, well, we know how to solve for an exponent. The only problem is this exponent is currently living in a denominator. And so to solve for it, we have to get it out of the denominator. So the first thing we do is multiply both sides by that denominator, so that it would no longer
Be in the denominator.
live. That's right. It will no longer be in the denominator. Then we're just going to do a little further algebraic manipulation. We're going to always choose the easiest way. So instead of distributing the 2,000, I'm definitely dividing by it. Much easier. What's the next step? That's right. We'll be subtracting 1 from both sides of this equation. And then, what do we do?
Divide by 4,000.
Yeah, divide by the 4,999 and then take the natural log. So we're going to get 0.8t, because the ln of e is just 1, equals the natural log of 1.5 divided by 4,999. And so to completely solve, t is exactly equal to this algebraic expression that means nothing in context of a word problem until we actually divide. Alright, so what's going to happen is sometime during this 10th day, we're going to hit that threshold to cancel classes. Okay, so the question reads, after how many days will college classes be canceled? Well, we could word that 2 ways. We could say after 10 days, classes will be canceled,
During your
or by the 11th day.
Yes.
Make sense?
Yes.
Okay, you try number 2. If you're not sure what to do, please let me know. I'll help you.
When it says estimate, is that, should we use an function for it?
Definitely. That's how you get an accurate estimate.
Is that 0.1656?
That number is 0.165. So you are correct.
plugged it into what I think is right, but I got a way different. Oh, you do?
Your calculator follows the order of operation.
Is it supposed to be that, like, on part B, that's just half the amount of months it is for part C? Like on part B, it's going from 100 to 500, and on part C, it's going from 500 to 100 to 900.
It doesn't always happen that way.
And did you just solve it?
It depends on what our numbers are here and what our decay constant is.
Did you just solve it for 900, and then you just put a greater than sign in front of the answer?
I solved it for 900.
Alright.
So I get 9 divided by 9 is 180 first. So that's how I get my answer. Natural log of 1 over 81 divided by negative. This should have a 6 at the end of all of these. Okay, so let's take a look at these. First of all, this is our equation. If we were to model this graphically, we know that at time 0, there'd be how many animals? How could,
100.
it would be 100, because if we plugged in 0, that would go away, and we get 1 plus 9 is 10, and 1,000 divided by 10 is 100. Does that make sense? Okay. And then our limit to growth is 1,000, so it's going to max out up here somewhere. So if we had to sketch a graph, that's a nice little graph. When we plugged in, did you guys get 177.29 or approximately 177 animals?
Yes.
Okay. And then for part B, it would happen, if we solved it algebraically, we get 13.27, which is during that 13th month or by the 14th. You could word it either way. Now I'm gonna look for 2 things on that. Is your math right? And did you answer the question? Okay? So, like on part C, is my math right? And did I answer the question? What does this mean? The population will exceed 900 animals. Well, that would be during that 26th month, which is by this 27th month. So you can word it either way. Yes, sir?
If the answer was like 26, if you rounded, it was like 26.00, like it was just 26, would you be able to say by the 26th month?
I would, yes, if it was that close. Okay, now, those 2 examples are just like the 2 beside it. Do you guys see that? So now we've done 2 just like what you're asked to do for homework. Now, I have 3 more examples. This first one is similar to number 1 on the homework, which happens to be on the back side. So if you just want to put this example over in that margin, do you see that nice little margin you got? If you'd like to put this example here. Okay, so the 2 equations we have going, we're going to choose the easier one to model. Okay? The initial value of the logistics function is 8. So that means at time 0, our value is 8. Does that make sense? Okay, the limit to growth is 56, so that means that m is 56. And then it says the function also passes through the point 114. So with all this information, we can find everything that's missing. So we have 1, 2, 3 things that are missing, and they gave us 3 pieces of information. We're good. So we're going to start by plugging in the initial, because that's nice, because I plug in a 0 for x, which makes b go away, doesn't it? Okay, so let's do that. And we also know m already. M is 56. So I'm going to say 56 equals 1 plus a times b to the 0. And what is the y value when x is 0? 8. So it equals 8. Well, b to the 0 goes away. So when I multiply by this, I end up dividing by the 8. Don't distribute that 8, I just immediately divide by it. And so I get 1 plus a equals 7. And so a is 6. Okay, so now I have another piece of the puzzle. I know that a is 6. So let's plug in 6 now. So I know m is 56. I know a is 6. And b, I don't know. But I have an x and a y, and look, I've got another x and another y. So let's go with that one. This is 1, this is 14. And this is easy to solve for b. So we get 1 plus 6b equals 56 divided by 14. So 1 plus 6b equals 4. 6b equals 3. B equals 1/2. So I have m, I have a, I have b, I have everything I need. So my equation is y equals 56 over 1 plus 6 times 1/2 to the x. Make sense? Okay, the next one is very similar, but instead of this point being 1 something, it's a different number. So there's a slight, we have to do something slightly different at the end, but the beginning is the same. So once again, they tell us the initial value is this, so that indicates that this is a point. The maximum growth is 120, and it passes through this point. So we have m of 120. We have a point at 0.24 and a second point that this function passes through at 0.30. So when I plug it in, I get 24 equals 120, 1 plus ab to the 0. Okay, now I can look at this and not even algebraically solve and get it, because I know that 120 divided by 5 is 24. So 1 plus what is 5? 4. But you may need to show a little more work. You may need to multiply, and you may even need to show this. If you need to show every step, show them. At this point, I don't always show every step. There we go. So we get 4. So now I have m, I have a, all I need is b. So I'm going to use this last point to help me find b. So I'm going to plug in what I do know. I know this last point is 30. I just saw for a, it's 4. But this time b is going to be raised to what power? 3. So b is raised to the 3rd power here. Okay, we're going to cross multiply. And then divide by the 30. I'm going to subtract the 1. And then divide by the 4. Now, I do not know what the cubed root of 3/4 is, so since it's not pretty, what I'm going to do to solve is to raise this side to the 1/3 power. Because does that solve for b?
Yes.
And whatever I do to one side of an equation, I must also do to the other. So what I get here is that b equals 3/4 to the 1/3. Now I got it all. I got m, a, and b. Let's plug it in. Y equals 120. 1 plus 4 times 3/4 to the 1/3 to the x. 1/3 to the x. Could I write that as x divided by 3? Yes. There's my answer. Okay, the last one we're not even going to do the whole thing because it gives us the exact same information but in graphic form. This is when I punch the equation for this into the calculator, that's what it looks like. Pretty cool, huh? So this is my sketch of this function. What is my limit to growth? What is m? 40. And then do you see I have the initial amount of 4 and I have another point. So it is just like example 3, except we have to get the information off a graph instead of being given the information. Okay, I'm going to pass back the cooling lab so those of you that need more time to finish can finish. Okay, your homework is to finish that logistics worksheet. Some of you are not going to be here on Friday, and I have Friday stuff already ready for you so you can get a head start on it. So if you are not going to be here Friday, come pick up this worksheet, circle problem worksheet. And if you need the cooling core slabs, I have those for you.